Thank you very much. You'll be relieved that we do have exams. They were lost. They were lost this morning, so they made me new ones. So I know that's all right. Here we go. So there's one more thing. There's a question on the exam on this next slide. Ready? Here we go. You can do it. So don't just copy blindly. You got to listen and understand what we're talking about, right? So maybe in your own words, or if you're able to listen and write at the same time, make sure you're comprehending what I'm talking about. Okay. So here's another kind of surface. What do we cover? Ellipsoids, paraboloids, spheres, double cones. These are all things we talked about, right? Planes. Those are all. So here's another kind of surface, which we call a cylindrical, not cylindrical. Cylindrical surface, or cylinders. So this is any surface that has a constant cross-section if you move in some direction along the surface. Like, no matter how you slice it, you get the same curve. Make sense? Okay, so how would you form one? You just take any planar curve that you want, and then you translate it in the direction normal to the plane. So you just take the curve in the plane, and then just translate it, move it perpendicular to the plane that it started in, and that'll generate a cylinder. Make sense? All right, so here, so the most basic ones, the easiest ones, are any equation of two variables graphed in R3. If you take an equation of two variables in R3, like y equals x squared, z equals cosine x, or z equals e to the minus y, and then the missing variable is just allowed to be anything, right? And so that's our translation, and then you get a cylinder. So let's watch. So let's take for instance, z equals cosine x. Okay, z equals cosine x is this. Do you see how that's z equals cosine x? All right, so what we want to do is we want to think about just moving what z equals cosine x in the direction or orthogonal or normal to its plane, which is then in the y direction. And so when I do that, imagine it sweeping out a surface. See that? So now that yellow surface is a cylinder. Is a cylinder like a... So, when you think cylinder, do you think this? Did I just change your thoughts? Okay. Any curve can generate, any planar curve can generate a cylinder by taking it, translating it normal to its plane. So that's the cylinder, or the surface, z equals cosine x. So no matter what y is, you get the same thing, z equals cosine x for every y. Doesn't make sense. Another example. Here's the other example I had. Z equals e to the minus y. So now you're looking right at the yz plane, right? X is coming straight out at you. That's the graph of z equals e to the minus y. So again, we want to think about taking that thing and moving it in what direction? In x direction, right? That's orthogonal to the x direction. Like this. And when I do that, it sweeps out a surface. That's a cylinder, okay? That's the cylinder, z equals e to the minus y, or the cylindrical surface. So why don't you, for your blue sheet, why don't you sketch the cylinder y equals x squared. That's the first example I gave you. So this is question number 2 on your sheet. Sketch y equals x squared as a cylinder. So if your artistry is not great, at least it has to show the spirit of it, okay? Maybe think about it to yourself, and if you can't make a good rendering of it, then look at someone else's and maybe get some clues for good sketching, okay? So y equals x squared. What would that look like in R3? Z equals x squared to me. See what I'm saying? Yeah, that looks like you drew Z equals x squared. Y equals x squared. Y equals x squared. Okay, let me give you a hint. Here's how I can make a good start. There's a hint. There's a hint. I can take it from there. Okay, 30 seconds to check. This is it. Okay, so I should talk about this. Let's go ahead and talk about this very first question before we move on. So this double cone looks like this. And how do I write the equation of just the top or just the bottom? Kyle knows. None of those guys know. Yes, sir. Yeah. Okay, if you take the square root of both sides, you get z equals square root of x squared plus y squared, right? Nope. Square root of both sides, like you said, plus or minus. So you just got two equations, right? Z equals the square root, and z equals minus square root. What about using absolute values on this? Has no effect, right? Has no effect. Everything's positive here. When you square something, and then when you square things and add them, you got all positive. So taking absolute values is going to have no effect on the original equation. We need to separate this out into the top part, which is z equals positive square root, and z equals negative square root. And so then all these z's will be positive, right? Because if you take the square root of a positive number, you get a positive. Take the square root of a positive number and then take the opposite of it, it'll always be negative, right? So this is the top cone. This is the bottom cone. Right? Mirror image across the xy plane. Okay, so we're ready to start new material now. So that was all that stuff that we've done so far in class is fair game on your exam. Any questions? Okay, so when we talk about multivariable calculus or vector calculus, it really boils down to two things. Or not two, but a big part of it is surfaces in space and then vector functions in space. And there's all kinds of different vector functions, and we're going to look at different types. But the very basic vector function is the one we'll start with. Okay, and so vector functions are of this form. So you'll see the r with the vector. So since this is a vector function, this could be r with the arrow, or it could be the bold r, right? So you'll see in both ways. But usually when you're writing, it takes too long to write in bold. See, I'm still making the r. Okay. So you'll see it both ways. Okay. You'll see it with the arrow on top, just like you saw vectors. Okay. And so it's of the form x, y, z, where x is a function of t, g is another function of t, and h is still another function of t. Or some of those could be the same, but you have any function of t for each of the three components. Okay, so this is one type of vector function. In this type of vector function, how would you characterize what is the independent quantity, variable, thing? What is the dependent quantity, variable, thing? What is it? So what's independent here? What kind of thing is independent? We can choose freely to vary it. What kind of thing is that? T. And what is T? Yeah. What kind of thing is T? What is it? Is it free variable? Okay. Is it a vector? Is it scalar? What is it? Is it a vector or a scalar, T? Scalar. It's just a number. It's a real number. Okay. So our independent variable in this type of vector function is a real number, T. Okay. Then what do we get from a vector function? So so for every real value T, the dependent thing that comes out of a vector function is what? The vector, right? It's a vector. So you give it a scalar. For every scalar, it gives you a vector. That's what this type of vector function is. Okay? And so notice that I could really express the exact same thing this way. So if I wrote these three things, would you agree that it expresses exactly the same mathematical idea as this horizontal statement? Would you agree with that? So what is this? It should look very familiar. Yeah, this is parametric function, right? It's just so a parametric function and this type of vector function are like identical twins. They're virtually the same thing. And you've seen this before in Calc 2. Now it's just we have got one more. We've got one more function in our group. So I think we saw just saw R2 parametric functions in Calc 2. And so now in R3, you've got one more dimension. So it has its own function, h of t2. All right, so vector functions and a set of parametric equations are really just so close to the exact, they express the exact same thing, just in a different way. Identical twins, okay? All right, so now you can talk about the domain. The domain is all values of t that result in a valid vector, okay? So if we need to get a valid vector, then question. So the domain is all values of t that make all of the components x, y, and z defined, or any of the components x, y, and z defined. So is it good enough that just at least one of them is defined by every value t, or do all three have to be defined in order to be in the domain? Yeah. So if I have a value of t that makes x okay, and y okay, but say z is undefined, is that in the domain? No, because it won't give me a valid vector, right? It won't, so then, because z would be undefined. So we need all values of t that make all of them true. Defined, sorry. All three components have to be defined so that we get a valid vector. So basically, it's just like the domain problems you did in pre-calculus, but you have to do it 3 times, and then you're going to take the union of the 3 domains, or you're going to take the intersection of the 3 domains. You're going to take the union, meaning all values of t, this or this or this, or you're going to take the intersection of the 3 domains. You need the intersection, right? You're going to need the intersection. You need all values of t that make all 3 of them defined. And that's your domain of the vector function, because you need to get a valid vector, meaning you have to have 3 valid defined components. Okay, does that make sense? All right, so let's see this thing in action. So what do we say? For every scalar, we're going to get a vector, right? And so then we're going to continuously increase the scalar, and then the vector is going to change, right? It's going to change with the x, y, and z coordinates, components are going to change according to f of t, g of t, and h of t. Any questions before I take this slide off the screen? Okay, so I got a cool one here. So here's one. So it's written vertically there. It looks a little bit more like the parametric version form, but you could easily write it horizontally. Okay, so I've got x is cosine t, y is this polynomial, and z is 0.5 sine of 5t. Okay, so for every value of t, and if you look down here at the bottom, this slider thing that I have here, n, is also the value of t. So right now the value of t is negative 1.15, and I have this vector here with a very large y component. You see that? So when you put a negative 1.15, y is much bigger relatively compared to x and z. Does that make sense? And I'm getting this large vector. But as I increase t, so every time I increase t, I get a new vector. Here's t equals negative 0.72. And here's the current vector. And we want to think about, so when we think about graphically these vector functions, we want to think about always position vectors. Put all the tails of these vectors at the origin. And then something happens when we do that, okay? So for every t, as t increases, I get another vector. So here's the vector I get when t is 1.58, according to those 3 equations, according to the parametric equations. All right, so what happens with this? If all the vectors we graph as position vectors, then the tip of those position vectors, the tips, then sweep out a curve in space. Does that make sense? So if you make them all position vectors, put the tail on the origin, let t increase, and the tips of those vectors will sweep out a continuous curve if those are continuous, individually continuous functions. So it's you kind of think of it. So you can think of it as the vector function as a set of vectors. But if you make all those vectors position vectors, it's a curve in space, a vector function, this type. So let's see the curve. This is a cool one. So here it comes. Ooh, that looks fun. Okay, so that was t from this. I'm showing you t from about negative 1.25. T is increasing now, sweeping out all the vectors, sweeping out points in space until there's t is 3.5. Okay. So you could, because you have 3 equations and you're working in space, by combining different types of equations, you can get some pretty crazy curves. Okay, let's look at another one. Here's these are all variations on trig functions. So you see up there, then shaded in blue is the function, and then you just get this crazy thing, right? It's crazy curve. Yes, sir.
Does this have like previous trig functions between the 2D plane that will eventually repeat itself?
Yeah. So if all three are periodic, then as long as you let t run far enough, it'll start over eventually. Yeah. Unless they're but they'd have to be periodic with a least common multiple, right, of their periods, right? If their periods were irrational numbers, then it wouldn't repeat. Maybe it wouldn't. So you'd have to have like, if you had rational periods, all three had rational periods, then it would eventually repeat. But if they were irrational, it wouldn't. Okay. I think I have one more. Do I have one more? Yeah. So here's a little simpler one. Here's x equals t, y equals sine 2t, and z equals 0.5 e to the t. Okay? And so what I want to show you here is that these curves then you can project them onto the different planes, and something interesting happens. So let's think about this. What will happen? So here's this curve, right? Let's give it a spin here. So here's this curve according to that vector function. So what do I want to do? I want to project this onto the xy plane. I want to project this onto the xy plane, meaning I'm going to look from above, up on z. I'll look down on this thing. What will I see? So I'll be only looking at what plane? So I'll be only looking at the xy plane. I will not see the changes in z, right? I won't see the changes in z. So I'm just going to see this, where x is t, and I think back to your parametric equations. In Calc 2, what is that? What curve is that in the xy plane? Y equals sine 2x, right? So this is just a parametric, an easy parameterization of the curve y equals sine 2x. And because of that, by looking down and projecting in the xy plane, we take the z changes out of it. That's what happens. So I'm going to come here and I'm going to project it in to the xy plane. And there's y equals sine 2x. Can't see the z's, right? If you can't see the z's, you're just going to see what you have in x and y. And we know we have in x and y equals sine 2x. Okay, so what if I look in the xz plane? What if I look in the xz plane? What am I going to see? Z equals 0.5 e to the x, right? Again, an easy parameterization of z equals 0.5 e to the x would be x equals t, and z equals 0.5 e to the t. So I'm going to come here and look in the xz plane. I want to make x positive, so I'm just going to rotate it right up like this. Here we go. So this is now looking at the xz plane. Pretty cool, huh? That's pretty sweet. So the projections are kind of like the different faces of the function. So what about the yz plane? Sine of 2t equals 0.5 e to the t. Nothing basic, right? Nothing basic. But let's look at it. So if I look at the yz plane, I'm going to get something, that's sinusoidal, but then it's going to get bigger with larger z, right? So all that stuff should pretty much go away here. Like that. So what's happening? It's sinusoidal, but because of the e to the t, as t increases, z is gonna, it's gonna get, it's like continuously increasing period, right? Let me zoom out once and see what happens. And pretty soon, the e of the t is going to dominate, and we're going to hardly see. For large values of t, and giving us large values of z, we're hardly going to see sine anymore. Okay? Okay, so this helps us to sketch. This helps things like looking for things like this. Helps us to, given a vector function, be able to make a sketch of it, right? Easy ones. So that is your task here. Okay, so they start easy, and they get harder. So you got to put your heads together here and make a sketch of each one of these. Start at the top. Make a sketch of each of these vector functions just from your knowledge of R3, your knowledge of parametric functions. What is not allowed is to make a table of values and put a bunch of t's in and then crank out the vectors. Okay, so I'll do two requests. So by popular demand or consensus, which two do you want me to talk about of these? All right. Okay, I'll give you 4 for free because I'm worried about you guys on this test. What is 4? This is exactly what we said, the parametric equations of a line. So you immediately know what? The direction vector is 3, negative 1, 1. It's a negative, right? Okay, 3, negative 1, 1. That's the direction. That's a vector parallel to the line, and you have a point on the line. When t equals 0, you know that your point is 1, 0, negative 2. Okay? So, if you those who recognize that, saw that, could identify those things, okay? That's good. If you didn't, then we'll see how the test goes, okay? All right, and then of 5, 6, 7, and 8, what's any requests? 7 and 8. Okay, so let's do one of these two. Let's do either 5 or 6. 6. Okay, so 6 lives where? Where does it live? Where does the curve live in number 6? X equals 2 plane. How could you describe the x equals 2 plane? 2 units in front of your paper, or 2 units in front of the board, like this. Parallel to the board or the screen, 2 units in front. So that's where that lives. And what curve lives in the x equals 2? Z equals e to the y. And so it's going to be here in 2. And so imagining in that plane right there, x equals 2, that cuts through the axis right there at that point, you're going to have z equals e to the y, right? So that red curve in that black plane, the black plane of what, x equals 2? Does it make sense? That's what that parametric curve will be. The red curve in that black plane of x equals 2. All right, number 7. So we want to think about, in 7, let's think about the projection into xy. What will the projection into xy be if x is cosine and y is 2 sine? What will that be projected into the, is that a circle? Ellipse, right? It's twice as wide in y as it is in x. So it's basically the unit circle, but stretched into an ellipse. So that's what you're going to see if you look straight down on that thing. But then as t increases, so as t increases, we go around that ellipse, and then what does z do? Goes up. So what are you going to get? Elliptical spiral that goes up. So this is the kind of thinking that you got to kind of use different things. So, and it's wider, so it's the projection is something like this, right? Right, twice as wide in y than it is in x. And so then, how do you draw? So you've got to keep it above that, and then z is going to go up at a changing rate or a constant rate? And let's just get the right point at 0. At 0, we're going to have 1, 0, 1, right? Or is it 0? 1, 0, 0. So we're going to start here. And we're going to go This is the standard x is cosine, y is sine, so we're going to counterclockwise. So it's going to do something like this. Or I could just turn it on. So it's an elliptical spiral that goes up on the z-axis. Again, if I look at the xy plane, I just get the ellipse. I just see the ellipse. And then if I look at the zy or the xz plane, I'm just going to see sinusoidal curves, right? T and cosine. So this one's going to be cosine, the other will be 2 sine. Which one is this? This is zx. 2 sine. Question on that. So do you kind of get in the hang of the thinking behind these to sketch these curves? Okay. So let's take a